One moment here. Your deal, vacuuming camera. Why are you so finicky today? All right. Where are we at? As you guys all have a midterm on Wednesday, right? Okay. And I'm assuming you're still talking about systems of non-linear differential equations. I know we talked about that a little bit last week. I don't think there's really anything else to talk about before your midterm, unless I'm missing something wildly. Seem plausible, right? Okay, so I guess yeah, I guess let's start. Let's do a couple one or two more examples of classifying equilibria of a nonlinear system of differential equations, and then we can kind of see where to go from there. Sorry, 1 second here. Yeah, we can look at this one, right? We didn't do this one. Let me double check my brain. No, I think we did do that one last time. We definitely did that one last time. Did we? Sorry, it's hard for me to remember all the things we did. No, yeah, we did do that one last time. All right, let me grab a different example here. Sure. Let's write some things. Co-17C. Today is the 13th of November. So more on classifying equilibria of nonlinear systems. Someone's right. Of nonlinear systems of differential equations. All right, so let's look at this example. So let's say we have, sure, we have the system dx dt is equal to 2x minus x times y, and dy dt is equal to, let me think for a second here. I don't want this to play out. Sure, let's say 8y minus x squared. And our goal for this question is to find and classify the equilibrium. We might also, after that, talk about the linearizations of each of the functions around the equilibrium, but that feels less important in my opinion. So, first step, let's find all the equilibria. So if I was finding the equilibria, I would start by setting each equation equal to zero, and then I'd probably try to deal with one that looked easier to me. And in my opinion, the first equation looks easier to kind of derive something from. So if I take this first equation, 2x minus xy, set that equal to zero, I'm going to factor out an x. I'm going to x times 2 minus y equals zero. So my values that make this first differential equation equal to zero are either x equal to zero or y equal to 2. I know I say it almost every time, but I'm going to say it again. 0 comma 2 is not an equilibria, right? We know that 0 for x or 2 for y make this equation equal to 0. But if you set x equal to 0 and y equal to 2, the second differential equation will not equal 0. So it is not an equilibrium. So we're going to take each of those and substitute them into the other equation. So we have first setting x equal to 0. We're going to have 8y minus 0 squared equal to 0. So we're going to get y equal to 0. And it's not a given, but it is very, very often the case that 0, 0 is still going to be an equilibrium for these nonlinear systems as well. Doesn't have to be, though. So 0, 0 is one over equilibrium. And then plugging in y equal to 2, we have 8 times 2 minus x squared equal to 0. So we have 16 equal to x squared. So we get x equal to plus or minus 4. So here are our three equilibria. We have 0, 0, and positive 4 comma positive 2, and negative 4 comma positive 2. These are our equilibria. Now, let's go through the process of how we classify them. So to classify them, all we need to do is find the Jacobian matrix and then plug in the equilibria and analyze it like we usually would for a regular matrix of a linear system of differential equations. So, step 2, find the Jacobian matrix. This does require us in some way, shape, or form to look at our original systems of differential equations and say, okay, we're going to call the first one F. We're going to call the second one G. That's pretty standard choice. And then our Jacobian is going to be the matrix of partial derivatives Fx, Fy, Gx, Gy. There was something else I wanted. Oh, sorry, you can't see what I was writing up there. Apologies. I keep feeling like there's something else I want to say, but no, I guess not. Okay, cool. So to find our Jacobian here, well, our fx is equal to the partial with respect to x, which is 2 minus y. Our fy is going to be 0 minus x times 1, so negative x. Our gx is going to be 0 minus 2x. And our gy is going to be 8 minus 0. So our Jacobian matrix is equal to 2 minus y, negative x, negative 2x, and 8. In step 3, plug in your equilibria, each equilibria, and analyze the matrix. I'll say analyze as usual, meaning you can either use the trace determinant method or you can find the eigenvalues. I would generally default to still finding the eigenvalues. To me, that just always feels like the easier thing to do. Yeah, question. Uh-huh. So in the gx spot, right? I'm taking the partial derivative with respect to x. And the function was 8y minus x squared. So the derivative of the 8y part is 0, and the derivative of the negative x squared is negative 2x. And then for the gy part, the derivative of 8y is 8, and the derivative of x squared is 0. Well, which part? So when I'm finding gx, right, again, so my g function is 8y minus x squared. So when I, was that? You're right. G is the entirety of what dy dt is equal to. So, and in fact, I should, right, G is all of this, and f of x comma y is all of the first one, which is 2x minus xy. So we're literally just taking our system of differential equations and setting f of xy to be whatever the dx dt is equal to, and g of xy to be whatever dy dt is equal to, or whatever variables we happen to be using. So then I'm going to start with the easiest one. If I plug in 0, 0, j of 0, 0 is going to be 2 minus 0, 0, 0, 8. And already we know everything there is to know about this. We know that one way to talk about this is you could say both your eigenvalues are positive. Your lambda 1 is 2, and your lambda 2 is 8. Both are positive, which means we have an unstable node or a source around 0, 0. Alternatively, if you prefer, you could say the trace is 10 and the determinant is 16. and you're in a place where you're in unstable land and you can compare the value. See, that's already too much work, right? I don't really want to compare those values to see if I actually have a, oh my gosh, spiral or a node. I don't like doing that work personally. All right, let's look at the other two. So the other ones were 4 comma 2 and negative 4 comma 2. So I plug in 4 comma 2, I get negative, not negative 2, I get 0. It's 2 minus 2. I get negative 4. I get negative 8, and I get 8. And here we do have to do the work of finding the eigenvalues or whatever you care to do. Um, Interesting. So I'm going to find the eigenvalues, but I just want to point out that if you look at this, what's the trace of this matrix? I know you guys know how to do the thing you would have to do to find the trace. It's just whether or not you know what it is you have to do. So to find the trace of the matrix, so I'll tell you here, the trace of this matrix was 10. So what's the trace of this matrix? It's 8. It's 0 plus 8. And the trace being positive means we're going to have instability. Also, our determinant here is 0 minus 32. Oh, we shouldn't even look at the trace. Our determinant's negative. We know we're going to get a saddle. I'm still going to do the work of finding the eigenvalues, but one thing you can do here is note that your determinant's negative. You definitely have to have a saddle. Let's find the eigenvalues anyway. So, eigenvalues, determinant of negative lambda. Ooh, negative lambda. That's how that looks. Yeah. Negative 4, negative 8, 8 minus lambda. My eigenvalues might not be very nicer because I totally made this problem up. So let's see what happens. It's going to be negative lambda times 8 minus lambda minus negative 4 times negative 8, which is 32. Set that equal to 0. Multiplying this out, you get lambda squared minus 8 lambda minus 32. And I don't think I can think of any numbers that multiply to 32 and add, sorry, to negative 32 and add it to negative 8. Yeah, I'm pretty sure that we don't get there. But let's not bother worrying about whether or not we can factor this since it's not immediately obvious and just jump straight to the quadratic formula. So here, lambda is going to equal negative b, which is positive 8, plus or minus the square root of negative 8 squared minus 4 times 1 times negative 32, all divided by 2. So check this out. We have 8 plus or minus the square root of 64 plus something, plus I think 128. I don't really care what that number is. Here's the point. 64 plus something is bigger than 64, which means that square root is bigger than 8. 8 plus it is positive, 8 minus it is negative, because that thing there is bigger than 8, which wholly directly comes from the fact that the determinant was negative. That's what's shooting us down this path of the eigenvalues having to be opposite signs. So we know that we have lambda 1 being positive and lambda 2 being negative, and that tells us we have a saddle.
For the b value, shouldn't it be negative?
For the which value? So b is negative 8, and the quadratic formula says we take negative b, which is negative negative 8, plus or minus the rest of the stuff. And it's a good thing to look at, right? Because that would definitely change the value of what's happening. Right. And that actually kind of goes back to my previous thing I said, which is I noticed that the trace was positive 8. So I saw that we were going to have instability. Now, technically, I don't love that because really the instability is coming from the fact that our determinant is negative. So we have a saddle, not the fact that we are having a unstable node or an unstable spiral. Let's look at the last one, which I would be willing to guess is going to be similar to the one we just did because of the similarity in the values, but not 100%. So let's look at j of negative 4 comma positive 2. So we're plugging in 2 for y and negative 4 for x. So our j is going to equal 2 minus 2, negative negative 4, negative 2 times negative 4 is 8, and an 8 over here. And yeah, I think we're going to get the same result. because this matrix also has a determinant of negative 32. So I'll point out here that the determinant of this matrix is negative 32, which is certainly negative. And when the determinant's negative, we know we have a saddle. Or you could do the work of finding the eigenvalues again, but it's really, really practically the same work here. The only difference is that instead of negative 4 times negative 8, we have positive 4 times positive 8. That's the only difference. But really, this actually the same exact eigenvalues. Questions about any of that? I'm not sure what's going. People, I feel like this is free. I mean, I don't know what the room hasn't been free this time. Any other time this quarter? Why are they coming here now? I don't know. Anyway, so um, questions about any of this before we maybe say more about it? Yeah, not at all. If I can, it may. Well, we'll see here. Sorry, it's impossible. There we go. Okay, here we go. What else? So I did notice that at least one of the homework problems asked you about drawing some null clients. So let's take a look at the null clients for a second, just because I do think it is something we should talk about briefly. Let's see here. So back to the original system for a second. So recall our original system was the following. It was dx dt equal to 2x minus xy and dy dt equal to 8y minus x squared. The first equation, so I should say, to find the null clients, you're just going to set each equation equal to 0 kind of separately and see what curves you get. So setting the first equation equal to 0, 2x minus xy equal to 0, we factor out the x, and we get x times 2 minus y equal to 0. So our curves that are going to be our x null clients are going to be either x equal to 0 or y equal to 2. And on those, and I should point out, right, those are x null clients, meaning the lines along those, the direction vectors along those curves should be purely vertical. There should be no change in the x direction because we are literally getting them by setting dx dt equal to 0. So if we start graphing this thing, yeah, I got that from here, sure. So I have x equal to 0 and everything. So here's x equal to 0. And all my null clients are purely vertical, which is kind of, or all my direction things are vertical, which is kind of a pain. And then y equal to 2. So along this line, y equal to 2, all of my direction arrows are also, I didn't really want those arrows on the end there. Sorry about that. All of these are purely vertical. You might not actually need to draw this part. I just think it's good to think about that. Oh yeah, these are x null clients. So the arrows, whether they point up or down, they are pointing vertically. So, right, this is a dx dt equals 0. This is a dx dt equals 0. And then look at the other ones. It's going to be a little bit more interesting. So setting dy dt equal to 0, we get 8y minus x squared equal to 0. Or solving for a variable that makes it easier for me to graph this, we're getting 8y equal to x squared, or y equal to x squared divided by 8. And that's going to look like a typical parabola, just kind of squashed down a little bit, right? Because we're multiplying by 1/8 essentially. So I'm just going to graph a few points here, and let's use a different color. I have other colors. So, oh, there we go. So we get the point 0, 0. And then if x is 2, we get 1/2. Be like right here. If x is 4, we get 16 over 8, which is 2. To me, the parabola kind of looks like this. And same thing to the left. And just as I mentioned last time, your equilibria are the places where the different types of null clients cross each other. So we get an equilibria right here where the y null cline This is your y null line, dy dt equal to 0, where your y null line crosses your x null line right there at the point 4 comma 2, also at negative 4 comma 2, and also at 0 0 where the y null line crosses the other x null line. So it shouldn't be a surprise that these are equilibria where these null lines cross each other. I should mention, and this actually kind of goes with what I was saying before, this point here, 0 comma 2, where the x null line crosses the other x null line, is not an equilibrium. It doesn't make both derivatives equal to 0 at that point. Cool. Is there anything else to do with this? No, we're not going to do that. I don't think we can do that. Let me double check. Let me double check one thing here. Sure. Maybe we should look at that. Okay, so there's one homework question I'm noticing that asks you to kind of do a little bit more analysis here. So let's take a look and kind of see what's going on this whole kind of picture here. Where'd you go? Other pen I was using. How do I lose pen so easily? It's kind of impressive. There it is, right in front of my face. So again, along this graph, all of my direction vectors should be horizontal. And one of the questions your homework kind of asks you to look at what's happening in sort of each region. Now, I'll point out in the homework question, although you have the whole entire XY plane, the homework question is really only focused on what's happening in the first quadrant because it's asking about populations of things. It wouldn't only really make sense to think about the populations being non-negative, or really it's actually strictly positive. So even though there's other stuff going on over there, we're going to focus on what's happening in quadrant one, where we can imagine that X and Y are populations of some living things that have to be positive. So the easiest way to probably attack this is just to kind of pick points in each region. So let's pick a point like between this null line and that null line. Let's pick the point 1 comma 1. And then we're just going to see what's happening in each population by plugging it in. So we plug in 1 comma 1. We're going to say that dx dt is equal to 2 minus 1, which is 1. And dy dt is equal to 8 minus 1, which is 7. So we could say that at that point 1, 1, both populations are growing, right? X is increasing, Y is increasing because dx dt is positive and dy dt is positive. And the direction we'd be pointing in would be right and up, but way more up than right. So it should look kind of like that. Let me zoom in a little bit here. Now, here's the deal. You can keep doing this for the other regions, right, where you've crossed over, but here's what should happen every time. When you cross over this null line where the change in X is 0, what should happen, I think, is we should still be pointing up, but now we're going to be pointing left because we've kind of, well, let's find out. Let's pick the point like say 1 comma 3 and see what happens. So we plug in 1, 3, our dx dt is going to be 2 minus 3, which is negative 1, and our dy dt is going to equal, let's see, 1, 3, yeah, 24 minus 1. So slightly left and very much up, like that. Which makes sense if you think about how we drew these things before, because right, if I was trying to actually draw like the trajectory here, we would have the trajectory kind of going through this point here, and then along the null line, it would have to be purely vertical, and then it kind of changes direction and goes the other way like that. So that's what's happening there. So when you're crossing a null line of one type, the other thing changes directions. So I'm crossing a y null line, and the x direction changes from pointing to the right to pointing to the left. And so over here, if we went over to like this section over here, well, we're crossing a horizontal null line, so we can expect to go from pointing up and left to pointing down and left. Let's check though. It's good to check. So if we pick a point over here, like say let's pick the point 6 comma 1. Well, at 6 comma 1, dx dt is equal to 12 minus 6, which is 6, and dy dt is equal to 8 minus 6 squared, which is definitely negative something, negative 28, I think. So we're definitely pointing right and down. Right and down, right and down. Hmm. I don't love that. I feel like I made a mistake of some sort. Does feel wrong, James. Oh, well, here's why it's wrong. I plotted it in the wrong spot. I chose 6, 1, which is not a point that's up there. That's a point that's down here. Sorry about that. That one points that way. I should have chosen 6, 3. Apologies. If I choose 6, 3, my dx dt is going to equal 12 minus 6 times 3, which is 12 minus 18, which is negative 6. And my dy dt is going to equal 8 times 3, which is 24 minus 6 squared, which is going to be negative. So 24 minus 36 is negative, what, 10, 12? Sure. So we're going left and down, not left and right. Good. That's what I expected to happen. So this is kind of the direction things are pointing. So kind of interestingly, you can kind of see how the point 4 comma 2 is kind of acting like a saddle. Because if we start over here, we're kind of coming in towards it and then moving away from it. We start over here, we're kind of moving in towards it and moving away from it. So it agrees with what we talked about analytically by finding the Jacobian and analyzing what kind of behavior we have around that thing. So you can also kind of do this graphically. It just feels like a lot more work to do it graphically. And so what I was trying to say before I kind of got messed up here, is that whenever I cross one of these y null lines, the x direction should change. This one was pointing left, and then I crossed over to the other side, and this one's sorry, wrong words. When I cross this y null line, apologies, the y direction should change. I'm pointing up and left, now I'm pointing down and left. When I cross this x null line, the x direction should change. I'm pointing up and right, now I'm pointing up and left. We change from right to left. Here we change from up to down. Here we change from right to left. Here we change from down to up. So whenever you cross a null line, one of your directions changes. Kind of neat. Kind of. Okay. Before I forget, let me pass around the intended. Sure. Let me pause here for a second. What kind of questions do you all have? Like, does this nonlinear differential equation stuff seem relatively sensible, approachable? Are there things I'm not talking about that you wish I would be? The reason I ask is because I feel like we've kind of covered this quite a bit. And while I could give you more examples of it, I don't know how helpful you might find that. So here's a better question. What do you all feel like we need to talk about before you have your exam on Wednesday? Yeah. Sure. Yeah, those ones are interesting for sure. We can do another one of those. Now, I should ask all of you, does your instructor expect you to show the change of variables? Okay. Let me see something here real quick. Nope, I think these are all nonlinear. Sure. Yep, they sure are. Cool. Let me look over here for a sec. That's not what I wanted. Yeah. Sure. When you say word problems, what are you maybe like, I mean, what exactly do you mean? Like, like just kind of like what I think of when I think of the word problems for this class specifically are kind of like obviously the problems, lots of words that usually end up having constants that are not actual numbers. To me, that feels like it's one of kind of like the features of these word problems. It's like usually you're just given like alpha and beta or mu or right, like they're just kind of like say, here's the things kind of go with it. I mean, I don't know. It doesn't seem impossible, but I know from a grading perspective, it's not fun to grade those problems. So it's hard to say. In fact, actually, that brings up a good point. Let's go ahead and take a look and see what he has posted about your exam because he did post a couple things I think are worth mentioning. So he does give you, he said, here's the formula sheet for exam two, which seems like a lot. So if you take a look at the, ooh, okay. So taking a look at the formula sheet, you have things that seem like they're really not at all necessary, like this limit definition of the derivative. That seems odd, but whatever. And then some derivative rules that I feel like we all should know. Yeah, that just feels it feels like this is like the most general, like here's your formula sheet for any 17 A, B, or C class. I'm just gonna put the things on there that seem like you might need to know them ever. None of these seem particularly applicable to this class. Not that you wouldn't take these derivatives, just that it's not really the meat of what we're doing. On the other hand, the second page here does seem like it's got a little bit more of what we actually talked about. So eigenvalues of a matrix, the way you usually find them, quadratic equations, sure general solution for a linear system of differential equations, right? There's your typical way of doing it. Um, and then the linear approximation tangent plane equations, what I think you might actually mean there, not tangent line equation, because it's a tangent plane, not a tangent line, really. What's that? Sure. I mean, it's not like a terrible mistake to make, but it's just like it's easy to think because like when you first talk about it, it is a tangent line equation, then we extend it to a tangent plane equation, but it's still it's not something that's going to throw you off. So that's what he's giving you, and then we also have over here. So, in my opinion, the stuff on this, maybe this last one is an exception, but in my opinion, everything else on here you should already know. Like you know these things already. You know how to find eigenvalues and eigenvectors. You've done it a lot of times, and also seeing it written out here might not be super helpful. Like if you don't already know how to find an eigenvalue, seeing this equation here is not going to like help you do it. It might jog your memory. Like, oh yeah, where I need to put the things. But again, I feel like you all know this already. Um, I will point out, well, no, it does. And then it does show the way of finding the eigenvector the way I don't typically do it, but that's fine. You can do it whatever way you like, unless he says specifically you can't, but I don't think that's his deal at all. Some people are really particular. Like some people are like, you should do it this way, and I'm going to make you do it this way. Most most people mathematically are not like that, with maybe a few exceptions in the math department. Um, and maybe this tangent line equation I could see maybe coming up, and not something that I would particularly memorize. So that's or tangent plane equation. That might be the one thing that's like, oh yeah, I might need that on the exam, and I don't want to spend time memorizing it. Yeah. Yeah. I will actually point out though, because I do think it's worth mentioning. So let me just show you that equation. You actually kind of already know it. I wouldn't write it like that. I would write it like this. Let's move this over here for a second. So another way to write your tangent plane equation, and again, I'll point out it's not really f of xy, it's f of xy as a vector. So really you have your vector. So let me give a little more context here. So we're talking about our usual kind of system of equations where you have dx dt. So the classroom just got really loud behind me. Dx dt equal to some stuff, dy dt equal to some stuff, and then we say that dx dt is going to be our f of xy, and dy dt is our g of xy. So what we're doing is we're making a linear approximation of both functions at once. So it's our, oh no, okay. No, sorry, I see. So the equation I should back up. The equation he wrote is the equation. No, it's still a tangent plane. Yeah, okay. Yeah. So he's only writing one at a time. All right, cool. So let's talk about, so I'll do both here. So here's his tangent plane equation. F of x, y equal to f of, I'm going to write x hat, y hat instead of x naught, y naught, because usually we're plugging in equilibria plus your partial derivative evaluated at x hat, y hat times your x minus x hat plus your partial derivative with respect to y also evaluated at your point x hat, y hat times y minus y hat. So that is your tangent plane equation. This is the tangent plane, and I should fix one thing here. Sorry. This should be approximately equal to, right? We are approximating f of xy with this linearization. And similarly, you can write the exact same stuff for g of xy. G of xy is equal to g of x hat y hat plus the partial of g with respect to x evaluated. I feel like writing the evaluated part's not super necessary. You know you have to plug stuff in there. Times x minus x hat plus the partial of g with respect to y evaluated at x hat comma y hat times y minus y hat. I made the same mistake I did last time. That's approximately equal to, and then this is the linearization of g. But really, what we like to do is we like to write it as one big equation that has both of these equations at once as a matrix equation. So what you're really saying is f of xy and g of xy, which are just what these derivatives are being approximated by the linearization as a vector, which is the f linearization and the g linearization. And now check this out. Remember last time how we talked about how when you plug in these equilibria, this part ends up equaling zero because that's how we found the equilibrium was by setting each thing equal to zero. And I should say the thing I'm talking about here is specifically for the case where we're trying to describe what's happening around an equilibrium of a nonlinear system of differential equations. You can also talk about tangent planes in general, where this first equation is the right thing to do. But when we're talking about the linearization of a system of differential equations, these parts get to be zero because we found this equilibrium by setting each thing equal to zero. And look what we're left with. You're going to have your Jacobian matrix, fx, fy, gx, gy, times your x minus x hat, y minus y hat. Super cool. Kind of. It's kind of super. I mean, it's not okay. There's much better things, but sorry, I got a little off track there because I got kind of too interested in talking about that. But let's go back to the other thing which I want to mention was the other file I was looking at, which was your, where'd you go? I had you open. Sorry, one second. Hiding stuff for myself here. He also posted a thing about like just what's on your midterm, which feels like I've lost it. Wow, how did it, there we go, discussion sheets. Sorry, I was in the files earlier and they seemed much more well organized here. 1 minute. There we go. Exams. Midterm 2 material. Right, that's what we want. Yeah, so hopefully, well, you might, I don't know when you posted this, but we should all look at it. So here's what's on midterm 2. And basically it says systems of differential equations. So that's a clue that you're going to see a lot of systems of differential equations. Um, so let's see what we've got here. Be able to write a system of linear differential equations in vector matrix form. Okay, we've done that a few times. We're just taking the equations and writing as a matrix of coefficients times your xy or x1, x2, whatever it is. We have fixed points, also known as equilibria or steady state. You know how to find those. We found them a bunch. You're just setting each thing equal to zero and finding all the solutions. For linear systems, there's only one solution. 0, 0 if it's homogeneous, or whatever it is if it's non-homogeneous, which we find by setting them each equal to 0. Then we have understand what it means for a steady state to be stable or unstable. I think we know about that too. You know how to determine the stability or instability by, I would say, by looking at the eigenvalues is probably the easiest way, or the way, maybe not the easiest, but the way that makes the most sense. Direction field. Understand how the direction field in the phase plane is generated and that it is a graphical representation of the system of differential equations. Interesting. Okay. So I think the second part of this is a little more telling. Be able to use the direction field to approximate solution trajectories in the phase plane, and then plot corresponding solutions in y and x and y versus t. Okay, I can kind of see that being something. So, for example, do I have a good example off the top of my head? So let's say, and you can't see this just yet. One second. So let's say that we had a I'm not going to draw the actual direction field because like it's a lot of arrows to draw. But let's say we drew he gave you a direction field and then asked you to draw a trajectory on it, starting at the point maybe say like 2 comma 1 and following the arrows that are not I have not drawn, but we'll pretend like they're there. And let's say our trajectory looked like this. So we had something that was probably like an unstable node where everything is kind of zooming out away. So maybe things are doing like this and like that and like that, and maybe over like that. I'm just kind of making it up here, but specifically, we're interested in what's happening here. And then we're asked to kind of draw oh, sorry, I lost what I was going to say here. Apologies. We want to draw, go away. We want to plot the corresponding solutions. Right. Okay, cool. So we want to plot both x of t and y of t. So some things to know about this. We know that when we solve a system like this, let's pretend it's like a regular linear system of differential equations, which has the 0, 0 as the solution. So we know that our general solution is like c1e to the lambda 1t plus c2e to the lambda 2t, kind of it. So we can say, well, for the x of t, what x value are we starting with? 1 or 2? I think 1. Right? We're starting at the point 1 comma 2, the x value, the beginning, the initial x value is 1. And then as we move in this direction, our x value is getting bigger or smaller? Definitely bigger. So we would expect our graph to look vaguely exponential because we know it's e to the lambda t plus other e to the lambda t. And we don't have the solution written for us. So we're just kind of making a broad generalization here, but it's going to look something like that. As time goes on and on and on, the x values just continue to get larger and larger and larger, at least with that initial starting point. And similarly, if I want to plot y of t, it's going to have the same sort of look, except we're going to start at 2 instead of at 1 because my initial y value is 2. But then, maybe if you're looking at this, you're like, well, it's a little steeper, so maybe the y's are getting bigger a little bit faster. Maybe it looks more kind of like, that. But similar idea. There's not a whole lot more to say here, right? If we're just asked to do our x of t and our y of t plots given some initial condition and following a trajectory. That's all you can really do if you're asking. But I could see asking a question of this nature. Don't worry, I promise we're going to come back around and do a homogeneous example. I just think we should go through this first, and then we can do that. So so that's all I really want to say about that particular thing. Let's go back to what we're looking at over here. To know the different qualitative, there's so many words. Holy smokes. Okay. He likes to write a lot, I feel like. He's very verbose. Okay, it's all right though. It's not a bad quality. So let's see here. So know the different qualitative behavior of solution systems of linear differential equations, i.e., stable and unstable nodes, stable and unstable spirals and saddles. Understand how the flow in the phase plane indicated by direction field underlies the different behavior. Okay. I was good with everything up until the understand the flow part. We definitely know how to determine if something is a stable node, a stable spiral, an unstable node, an unstable spiral, or a saddle, or even a neutral spiral, right? Where your real part is zero. But understand how the flow in the phase plane. So I feel like if you're drawing a trajectory in the phase plane, indicated by direction field underlies the different behavior. I just feel like we're talking about like if you know it's an unstable spiral, you know it's like circling around and going outwards. Or if it's a stable spiral, it's circling around and going inwards. Or if it's a stable node, you're kind of pointing inward from every direction. For the unstable node, you're pointing outward from every direction. And for saddles, you're kind of going in and then away, or in and then away along your different eigenlines. But I don't know what else to say about that. There was one thing, but here's one thing I do think he could probably ask. To after you have found the, what am I looking for? After you've determined something is a stable or an unstable spiral, I could imagine him asking you about the direction your spiral is turning, whether it's clockwise or counterclockwise. So let's talk about that for a second. So, how to determine if your spiral is clockwise or counterclockwise. Well, oh, sorry, you can't see that. Sorry. There we go. Cool. So let's say we have the following system of linear differential equations. We have dx dt equal to, let me think for a second here. I want my, sure. Sorry, I just want to make sure these numbers come out right. So one moment, please. Sure, three. Sure, that'll be terrible. Fine. Okay, so we want dx dt to equal. Sorry, it's always weird to make this come out the right way. Um, X plus 2y and dy dt is going to equal. Think here for a second. 3. So, oh my gosh, my brain. Apologies here. Sure, -3. Right, and then sure. Yeah, that'll be fine. Okay, cool. -3x plus y. Sorry about that. So let's go ahead and find the solutions. Let's go ahead and classify the equilibrium, and then we'll talk about if it's a spiral, which I hope it is, which direction it turns. So first classify. All we're really going to do is find the eigenvalues. In fact, why don't you guys find the eigenvalues? It's good practice. Let's see what we've got here. So got 1 minus lambda times 1 minus lambda minus 2 times -3 equal to 0. And in this case, I would actually say you could kind of skip the quadratic formula because you have a 1 minus lambda times 1 minus, you have the same thing multiplied by itself. So instead of multiplying this out and then writing this as one quadratic equation, what you could do, it'd be totally fine to say you have lambda squared minus 2 lambda plus 1 plus 6 is plus 7 equal to 0, and then use the quadratic formula. But if you happen to notice you're in this lucky situation where you have 1 minus lambda squared plus 6 equal to 0, instead of using the quadratic formula over here, you can say, oh, look, 1 minus lambda squared equals -6. 1 minus lambda equals plus or minus the square root of -6. And then negative lambda equals -1 plus or minus I root 6. So lambda is equal to +1 plus or minus I root 6. Or you could use the quadratic formula over here and say that lambda is equal to -2 plus or minus the square root of -2 squared minus 4 times 1 times 7 all over 2 times 1. And that's 2 plus or minus the square root of -24 all over 2, which is 2 plus or minus 2 times the square root of -6 all over 2. Divide each part by 2, and you get 1 plus or minus the square root of -6, or 1 plus or minus I root 6. So either way, you get the same thing. But I will say, to me, this feels a lot easier if you happen to notice that you have something squared like that. It doesn't always happen, but if it does, I say take advantage. Yeah. No, good point. Excellent point. I was really simplifying this part to show that you got the same answer, but you're totally right. Once you get to this part, like right here, I would say that's enough to see that, oh yeah, my eigenvalues are definitely complex because I have a square root of a negative, and the real part is positive because that part's positive right there. So at this point right here, you could say, hey, I know that I have an unstable spiral. And I will point out that I will emphasize what you have pointed out, that if they're only asking you to classify this whether this equilibrium is stable or unstable, that's enough. If you can look at that and be like, yeah, it's complex, then you're good to go. Which I don't think is like a big reach. I think any of us should be able to do that just fine. But if you want to simplify it a little bit, there's nothing wrong with that as well. So now, how do we determine if it's a clockwise or a counterclockwise spiral? By testing points. I know we talked about this before, but it's something people often don't remember very well. So let's go ahead and see, how do we determine whether it's clockwise or counterclockwise? We're going to test we're going to test 4 points, but we're really only testing 2. We're going to test the points 1, 1, 1, -1, and then also -1, -1, and -1, 1. What I want to point out, well, I'll point it out as we do it. So let's test the point 1, 1. Test the point 1, 1. Dx dt is going to equal 1 plus 2, and dy dt is going to equal -1 plus 1, -3 plus 1. So our vector is the vector that's pointing 3 right and 2 down. So if I start drawing things, I go over to the point 1, 1, and I say, okay, I'm pointing right and down, a little more right than down. I'm pretty sure it's going to be clockwise. But I would say to show the person who's grading your exam that you've done enough work, it would be good to do a few more points. 1 point's enough? So 1 point's enough unless it happens to be kind of like if your vector was pointing like kind of maybe this way, it could be harder to convince yourself that it's clockwise or counterclockwise. I personally would like to plot one. Well, so I'm going to plot one more point, but it's really going to give me 2 more points. So if I do 1, -1, I'm going to get dx dt equal to 1 minus 2, which is -1, and dy dt equal to -3 minus 1, which is -4. So 1, -1, I am left slightly and down more. So I'm going kind of like that. And then, as I mentioned before, the points that are opposite should point in the opposite direction. So the -1 point should be exactly parallel to that one, but pointing the opposite way. And the -1 point should be exactly opposite that one, so pointing that way. And then I feel like your drawing is more convincingly showing that it's a clockwise rotation here. So it's definitely clockwise. And to me, that's the best, fastest, easiest way to do it that actually shows that you were doing something. It also should be noted. Now, I'll say one more thing. If you've gotten to the place where you know it's a spiral, then if you look back at your 2 by 2 matrix, which I didn't even write, if you look back at your 2 by 2 matrix, which would have been 1, 2, -3, 1, you can remember, but this is not sufficient to show your work, that if the upper right corner is positive, that's going to be clockwise. If it's already a spiral, right? If it's not a spiral, like you've got a saddle and that's positive, well, cool, but that doesn't mean it's going clockwise, or the saddle is doing a saddle thing. Or if it's a node, that being positive means nothing. But if you've done the work to see, oh, I've got a spiral going on, then that being positive shows it's clockwise, and that being negative shows it's counterclockwise. But that still isn't enough work shown to convince someone that you know it's doing what it's doing. You should draw the picture. But at least if you look at it, you'd be like, oh yeah, I know it's going to go clockwise. So you can kind of draw a picture real quick and then be like, cool. All right. Time is it? Okay, sure. Let's see what else is on this giant list of things that's on your second exam. Let's see. So we talked about the qualitative behavior. Okay. What else do we have here? Understand the solutions for a system of linear differential equations can be written as the linear combination of two solutions that involve. Okay, that's just the general solution. That's a lot of words to say. Know how to write the solution is C1 e to the lambda 1 t times V1 plus C2 e to the lambda 2 t times V2, which we said like 1,000 times in this class. Know how to apply the initial condition to the general solution to get a specific. So know how to plug in the initial condition to find C1 and C2, the constants. We've done that too, right? That's definitely something you're aware of how to do. Be able to classify the stability. Yep, we've talked about that a bunch of times based on the eigenvalues of the matrix of coefficients. Okay, yep, that's mainly how we do it. Understand how stable, unstable nodes, stable, unstable spirals, and saddles arise as a result of the eigenvalues of the matrix of coefficient of a system. Right, right. Again, I feel like you're saying the same thing a lot of different ways here. It's all right. Okay, this next part might be a little bit more intense. Graphical interpretation of solutions. Understand how the eigenvalues and the eigenvector of the matrix of coefficients determine direction field in the solution in the phase plane. Okay, so to me, that's saying like drawing the eigenlines. Has he talked about eigenlines at all? Yeah, no lines, sure. But like, you kind of need to draw the eigenlines too. So what we've talked about is how, right, if you do draw the eigenlines, right, those kind of act like asymptotes, kind of, right? If you don't start on them, you get asymptotically close to them, whether you're going in towards the origin or out away from the origin, depending on if it's unstable or stable. But you can't cross the eigenlines. You're kind of on them or you're getting closer to them. For system with the real eigenvalues, be able to sketch the phase plane with the flow along the eigenvector directions. So that's what I just said. He said eigenvector directions. I said eigenlines. Same thing. Eigenvector directions is just the eigenline. So yes, he wants you to be able to kind of draw. Well, he's saying you should be able to do lots of things.
I think he said on the test they'll be going for it,
Okay, cool.
but you have to know.
All right. And so definitely, right, you can find them. Knowing which eigenline is which is not too terrible, right? You literally just say, well, if your eigenvector is like 1, 2, then you go 1 in the x direction and 2 in the y direction. And whatever line is going through that point, that is the eigenline that goes with the eigenvector and its associated eigenvalue. And the eigenvalue tells you, so if the eigenvalue is positive, that means you should be pointing away or towards the origin. Away. If eigenvalue is negative, you point towards the origin. So both pointing towards or both pointing away. Yeah. For complex eigenvalues, understand that the imaginary part of the eigenvalues indicates oscillations in the system, which corresponds to the spiraling of trajectories, sure. And the real part determines whether the spiral is stable, unstable, and how to get the direction. Right. So here's what I would say about this. You know this as well. And we talked about it, not a lot, but we did talk about it briefly. So one thing to remember, so one thing of interest, this is a, so sure, note, smart James, real smart. So reminder that your solutions look like C1e to the lambda 1t times V1 plus C2e to the lambda 2t times V2. And if lambda is positive, the e to the thing here gets bigger. If lambda is negative, the e to the lambda thing here gets closer to 0. And if lambda is complex, so if you have e to the a plus bi times t, I know it's been a minute since we did this, but that breaks apart as e to the at times e to the bt times I. And the e to the I theta part here is the part that becomes cosine and sine. This becomes e to the at times cosine of bt plus I times sine of bt. So this part, this is what tells you, is giving you the oscillation, which leads to the spiraling. This other part, the e to the at, that's telling you whether it's stable or unstable. So stable, meaning getting larger, sorry, getting smaller, or unstable, getting larger. So stable, your A is negative. Unstable, your A is positive, right? You're growing larger and larger and larger if you're unstable, away from the origin, or you're getting closer and closer to 0 if you're stable, getting closer to the origin. And then this is making you circle around and around and around and around. So it's kind of, if you remember that this formula works the way it does, like you have e to the something times t, and the whatever you're multiplying by t really is determining whether you're getting small close to 0 or big away from 0. That tells you kind of everything you need to know about stable or unstableness. Stability or instability is maybe a better way to say that. What else? For the complex, sure, yeah. And also know how to get the direction of the spiraling in the phase plane with a test point. Cool. We're ahead of the game. In all cases, know how to use your approximate solution trajectories to plot the corresponding solutions x and y versus t. We kind of talked about that as well. Compartment models. Okay, we should probably do some of those on Tuesday. Know how to construct a compartment and analyze and solve a compartmental model for intravenous drug dynamics. Know how to solve system linear differential equations with additive, non-homogeneous constant terms as done in class. Okay, that's something we can talk about more on Thursday, Tuesday. And then the stuff we've been doing, wow, geez, so many pages, right? We've talked about all this recently, be able to find, so for non-linear differential equations, be able to find the fixed points / equilibria, understand what it means to be locally stable or locally unstable. So for local stability, right, we're looking at the Jacobian and, right. Okay. Sorry, I'm just reading the, right, be able to use the eigenvalues. So it's really, you're analyzing the same way, right? And again, the idea here is that we're essentially saying locally, this non-linear system looks like this linear system locally. And so then we can say locally, we can just analyze the linear system in the usual way to find the eigenvalues. That's what I believe he's saying here. I'd be able to use the eigenvalues of the Jacobian matrix to classify a steady state as a stable, unstable node, stable, unstable spiral, or saddle point, or a neutral spiral, right? That could also happen. And understand why the local stability of the steady state can be determined by eigenvalues because of the reasons we just said, right? Because this, as I just said, this nonlinear system is being approximated by this linear system locally. And so we're just analyzing it like it's a linear system, even though it is not general. Null lines, test points, which we just talked about. Be able to use your approximate direction field to plot approximate solution trajectories and then to sketch the corresponding solutions x and y versus t. Sure. So back to the one example we did before. So we could point out for this example we did earlier on, where'd you go? Sorry, I keep messing up where I'm at here. Right, for this example here, we could then kind of ask, so I should point out that down here, these horizontal directions definitely point rightward. Right, because it's right over here and it's right over here. So it has to be right here. And these ones definitely point leftward. And blue, where'd you go, blue? There we go. And these vertical ones definitely point upward. And these vertical ones definitely point downward. So then we could kind of ask, and again, sticking with just the first quadrant for now, we could ask to plot the trajectory based on some initial condition. So if I gave you, say, an initial condition of, I don't know, let's say we had an initial condition of, trying to make it somewhat interesting here. Let's say our initial condition was, 3, 3. Plot the trajectory. Well, we would start right here at 3, 3. Sorry, 3, 3, and see that we're in the region where we're going up and left. So that's the way we have to go. And we kind of just this is not it doesn't feel like an excellent choice really, but we're just kind of going to go that way. That's about as good as I can do. Right? There's not a lot, and so I should say, if you had more little arrows plotted, like if you were given a full direction field, then your trajectory should kind of follow each arrow as you move in that direction. So like there should be like an arrow pointing kind of this way here, and then this way here, and then that way there, so that we're kind of following that direction as we draw our path out. Okay. Let's see what else we have. With all the words that your instructor has written. Sure. You know how to do all the homework problems. The extra problems on Canvas and problems in the class. No big deal. Just know how to do everything, right? Suggested practice problems. Okay, cool. So here's stuff to work on. I would encourage you all to work on the problems he has posted here after you finish your homework assignment that's due, whatever day it's due. In a couple days? Yeah. All right. I don't have a good non-homogeneous problems off the top of my head. Can we wait? Can we save it till Tuesday, whatever day we meet again? Gosh, this whole not having class on Tuesday thing is messing me up. So I would say, yeah, I will come prepared on Tuesday to kind of review the things that we've just talked about reviewing. I would encourage all of you to work on those problems between now and then. And yeah, and let's call it a day. Give you 10 minutes of back of your time. So generous. Silly people say, give you the gift of time. All right, have a great day. Try to stay not too wet because it is wet out there. And I'll see you on Tuesday. Thank you. I will also say if there are specific things besides non-homogeneous that you really want to see on Tuesday, send me a message, either post something on Canvas or send me an email. I'm happy to tailor things to your liking. I will certainly come with stuff as well, though.